people. So I'll be giving a talk about branes and trace relations, which is based on work on my own in 23 and a couple months ago with Lewis Stanford. The idea that a large N gauge theory reorganizes into a string theory has a long and fruitful history, which dates back from Hooft and coming to full bloom in the AES-CFT correspondence. And in particular, a state labeled by gauge invariant words in a large N gauge theory is dual. This is a statement that we're very confident about. It's dual to some state consisting of closed strings propagating in a bulk space. So in this talk, I'll venture into the study of the following questions, albeit in simple BPS sectors. So what happens to the above large N statement when N takes some finite integer value? And what additional entries of the holographic dictionary define that finite N? And what is even a useful perspective to for the bulk theory at finite N? Where do we start? So at finite N, there's an apparent tension regarding the spectrum of states of the bulk and boundary theories. In the boundary gauge theory, states formed by exciting the vacuum with single trace operators are orthogonal at large N, but become constrained by trace relations when N is finite. For example, at N equals to 2, a single 2x2 matrix valued scalar satisfies this tower of trace identities, and so on, where every trace with x power greater than 2 can be decomposed in terms of sums of products of lower traces. Therefore, the total number of states at fixed values of the conserved charges and lambda decreases as N is decreased. On the other hand, in the bulk, non-perturbative states such as black holes and D-branes become lighter at finite G string. So we simply know more states that exist at finite N than at a given energy than at infinite N. So such objects, which are present in addition to the perturbative string states, would naively result in many more states at finite G string compared to those at small G string. But how does one reconcile these differing expectations? To avoid a paradox, okay.
Sorry, Jim, could you explain the meaning of what the paradox is?
The paradox is that at finite N, we simply we know that from the boundary gauge theory perspective, we know that there should be fewer states for a given value of the energy.
Right.
But in the bulk, we simply know more states at a given energy than at infinite N.
Why is that? How is this about expectation?
Why is that the expectation from the bulk? Because the masses of D-branes and black holes get lighter at finite N. I mean, if you extrapolate these the brane tensions or the masses of D-branes and squared masses of black holes and squared to finite values of N, right? There are simply more states that appear to exist.
Still don't understand why that is that non-perturbative.
Right. So let's take large N.
Yeah.
Then what do we know? We know that there are stringy states, those survive. We know that there are KK modes, etc. But at finite N, in addition to those, we have non-perturbative objects, which have which have masses that are excitable. So there's more access to, like for a given energy, as you lower the value of n, those objects just get lighter.
Start from below compared to the higher value and
Yes,
the branes.
yes.
And the branes.
And branes, yes. I'll be focusing more on branes, but there are aspects of this which is relevant to blackholes.
Yeah, branes that seems to be real, come down and look like the big most.
So, can I proceed? Yeah. So, it's typically to reconcile the differing expectations. It's typically posited that non-perturbative objects in string theory represent highly redundant descriptions of the same set of quantum states. And actually, these non-perturbative effects, which we do not quite understand, actually need to cut down the total number of states. So the expected upper bound on the single string spectrum goes by the name of the string exclusion principle. And while this principle is thought to be a generic feature, there is little quantitative understanding of the mechanism underlying this principle. So in my talk today, I will describe a bulk effect that sheds a new perspective on how the string exclusion principle is realized. And I'll propose a holographic dual of these non-perturbative contributions in the boundary gauge theory. So one relatively newer development that enables progress on these questions is a formula called the giant graviton expansion. And it's a formula that relates the BPS sectors of gauge theories and their string duals. So it looks schematically like this, where the Zn, which is the superconformal index of un s n equals to 4 superangles at finite n, is expressed as a sum over BPS indices of ADS5 times S5 in the presence of k giant graviton rings. So Z infinity is the index of S5 Kaluza-Klein modes, and this other factor, which we sum over due to the Kn and Z hats, their indices of K giants and their quantum fluctuations, which one can compute explicitly. So pictorially, the expansion looks like this. It says that.
Hi, Jihoon, I'm not able to see your screen properly.
Oh, really?
Yeah, can
Okay.
this fix? I don't see all of it. I just see the left half. Can this be fixed?
Yes. So
Yeah, screen sharing too, right? Yeah.
I am screen sharing through Zoom. I'm wondering if this works better.
Maybe change the option to the not Zoom screen, but desktop screen. Desktop.
Oh, I see. This one?
Yeah.
Okay. So
Is that better?
Yes, that works. I see.
okay, great. So I'll just skip my presentation like this. So okay. Is the slide visible?
Yeah, this is great. Thanks.
Okay, thank you. So pictorially, this expansion looks like this, where you have the finite n answer somehow for a reason that is very unclear, which is expressible in terms of the infinity times a series of contributions with increasing numbers of these giants. So by now, there are many interesting work demonstrating that such expansions hold in a broad range of contexts, including in the 1/16th BPS sector of n equals to 4 superangles and type 2b on ADS5 times S5. So namely, Unu in the audience has several excellent papers on this topic, especially with regards to the relation between the 16th BPS giant gravitons and black holes in that sector. So giant gravitons are BPS branes on R cross S3 that are supported by a large angular momentum induced from the background run potential. So actually, these branes were originally discussed in the context of the exclusion principle. As classical brane solutions, giant gravitons on S3 and S5 have a maximal size of order n, which translates to a hard cutoff on its energy and R charge. But I think the giant graviton expansion adds a new twist to this story. So to understand the properties of the expansion, we'll concentrate on the formula in the simplest half-BPS example, which in which this expansion can be written explicitly. The half-BPS sector of UN n equals to 4 super mils is a purely bosonic sector. Consists of the states that you get by exciting the vacuum with trace of x to arbitrary powers, but modulo trace relations if you're at finite n. And the left-hand side is the spectrum of these gauge invariants. On the other hand, the bulk spectrum in this formula seems to overcount the half-BPS spectrum of UN n equals to 4 super mils. So each term here overcounts what we know is the spectrum at finite. So these are the partitions. This is the series corresponding to a partition with some extra factors, etc. And each of these really overcount the finite n. So the overcounting is saved only by the overall minus signs that result in large cancellations between BPS spectra computed on different D-brane backbones for these giant gravitons.
And these minus signs have nothing to do with any index, because here you're just starting bosonics.
That's right. Yeah. So we're counting. Right. So one way to see that, which I'll explain shortly, is that minus 1 to the f has a specific definition in this context, which is that minus 1 to the f equals e to the 2 pi I r for any r, or e to the 2 pi I j I ranges from 1 to 2. If these were fermionic states, then you would see you would need to see half integer powers of q in order for them to be physical fermionic states. I'll explain a sense in which they can be thought of as fermions, but these minus signs, as I'll explain, are not coming from this physical fermion number operator. Here the picture is slightly different regarding the string exclusion principle. It's a consequence of the fact that there are delicate cancellations in the bulk spectrum, as opposed to some hard cutoff on the classical brane solution. So how did the signs arise? So this half-BPS Hilbert space is purely bosonic, namely the states have R and J integers. So minus 1 to the f could not have been due to this physical fermion number operator. Indeed, we'll concentrate on this issue, and we'll find that minus 1 to the k has a purely bosonic origin. To understand how the sign arises, let's consider the contribution of a wrapped D-brane to the half-BPS partition function. So there are a lot of special properties of the half-BPS scenario, right? We can compute this quantity in this manner because of the invariance of the half-BPS sector under changes in lambda. But such quantities have been computed in very non-trivial cases, including the 16th BPS sector. But the goal is to explain these minus signs. Today, I think the minus signs are in this formula is what's is the most interesting property of this formula, and contains some nice physics. And the reason for working with this half-BPS case is that manifestly it's clear that the objects we compute will be bosonic. So I want to work in a context where it's clear that these minus signs are are not coming from some fermions. Okay. So to this end, we consider a thermal ADS 5 times S5 twisted by a background chemical potential for the relevant R charge R. So if we're considering scalar X, then we would have a R1. The Euclidean continuation of the D3 giant graviton is wrapped on an S3 cross S1 cross S3 of the twisted ADS 5 times S5. The Branes solution sits at the center of ADS and wraps a maximal S3 and S1. So that's the brane we'll be interested in. So let's evaluate the one-loop partition function of this brane with bosonic action, given by the standard the brane action, dBi plus Simons. So this part is very simple. The on-top contribution of this brane, one can compute this, and it's q to the n, has n units of the R charge, but the half-BPS sector receives for the one-loop contribution, the half-BPS sector receives contribution only from two world volume scalars, phi and phi bar, that parameterize the transverse fluctuations of the brane in S3 and S5. So these are the scalars on the world volume of the brane in the bulk. So the giant graviton, which change the size of S3.
These are unstable.
Right. So I'll tell you that. Right. So we can take a closer look at the lowest harmonics on S3, S1 cross S3, and we observe that because we introduce a chemical potential, which is the only way to regularize this problem. So otherwise this would be zero mass, and the quantity will diverge. For mu positive, we observe that there are two bosonic unstable modes with negative action, and you can find that the higher modes are unaffected. Okay, so the unstable modes are a consequence of the fact that we introduce a chemical potential to make this quantity well defined. And so for this one-loop partition function of the brane to be well defined, the contours for the real and imaginary parts of these modes need to be Wick rotated to the imaginary axes. And the contour rotation introduces a factor of I for each unstable mode. Since there are two such modes, the one-loop partition function for a single giant has an overall minus sign. And I'll explain. So one of the big aims of the more recent paper was to explain, to have some principled reason for why this contour rotation is the right thing to do. So so isn't this just some trick to make this brane contribution well defined? Why is this the correct thing to do? So if you compute all fluctuations, then the one-loop brane partition function, this is what you get. But the term at n equals to 0 in blue comes from the constant modes on S3, and the two unstable constant modes on S1 cross S3 contribute the minus sign. So there are no other unstable modes that give extra factors of I, and this is also true if we instead consider the half-BPS limit of the contribution of this brane to the 16th BPS index. So, since these minus signs appear, whether or not you consider the index, this minus sign I claim is a purely bosonic phenomenon.
So what is P?
So P is e to the minus beta. So we defined this object as a projection to the BPS sector in the large beta limit. So we need to take P going to 0. So these are other modes which are present and which you can compute, but in the end, this is the half-BPS contribution.
But if I keep it, then is there a way to match this whole quantity to, because there is only, I see. So for non-zero P, it's not true that only the half-BPS
right
states will contribute.
Right.
Only sensible thing to compute is that we.
Yes, yes, yeah.
Which would be.
yeah, that's what's protected and that we can compare with whatever object we know in gauge theory. So, okay. So why should the rotated contour give the correct contribution to the defining contour of this problem?
Sorry, why did you say that only the zero spherical harmonic on S3
Yes.
is unstable? Not
Yes.
not the higher spherical harmonics?
Yes.
Why is that?
So you can just read it off from the mass. So do you want to, are you interested in the mathematical explanation just from reading it off from the mass, or?
Yeah, sure. To start with, you're saying that the momentum beats the negative part.
Yes.
Okay, and
Sorry. So I didn't get that comment.
yeah, so you're getting some positive contribution because it has momentum on the S3, and a negative contribution because of B. And you're saying the momentum, when you got angular momentum 1 and higher, is always larger than B. Is that right? Larger than the negative from the mu square.
So momentum as in
Sure.
R. Oh,
The kinetic energy. The
yes,
The S3.
S3.
on the S3.
Yeah.
Seems like in that expression, there's a positive term coming from the kinetic energy and a negative term. No. That one.
Yeah, so these are just the higher masses of the spherical harmonics on S3, and then
So that's like del square. K plus 1 square is like del square for the spherical harmonic.
yes.
Right. Okay, and physically, what I'm trying to understand, physically, these oscillations would have been taking you away from half-BPS sector?
Yes. Oh, wait, you mean the oscillations in the transverse direction of S3 and S5? No, they are half-BPS.
I thought you wanted I thought the only half-BPS operators were Zs, things made out of Zs. And these guys, aren't they introducing X's and Y's into the mix? If you oscillate that.
So for general oscillations, I agree. But if you're just decreasing the size, if you're just looking at the modes which decrease the size of this S3 and S5.
Yeah, if you just decrease it in a uniform way,
Yes,
that's clear.
that's right. Yeah,
That's the zero.
yes, yeah.
That's why I was thinking that things that fluctuate, that has non-zero spherical harmonics, that's doing more than just.
Yeah, so there are other contributions, but these are the only relevant ones. So the other modes are captured in the other scalars. So either this or there are also AS5 scalars.
So in the end, everything other than this part cancels out.
That's right. Yeah.
Fine, yeah.
Yeah. Or you just truncate. Yeah, they're not canceling out. It's just
Because they're not protected, you don't want to count them.
that's right. Yeah.
I mean, the P part is.
Yeah.
Yeah, you just look at the P equals the zero limit of this
Yeah.
one.
Right.
So that's the only relevant piece.
Right.
Yeah. I mean, yeah. So we want to compute half-BPS answer. Okay. So why should the rotated contour give the correct contribution to the defining contour of this problem? In other words, in what situations does a saddle contribute with a minus sign to a purely bosonic path integral? And the phase space path integral treatment of this problem will be more illuminating for answering this question. So for a single maximal giant, the phase space path integral for constant scalar modes on S3 of the giant can be expressed as, after some massaging, in this form, where Z equals to P plus IQ, where these are combinations of momenta and positions of the 5 fields are there. So ordinarily, this would be a path integral quantizing the phase space R2 with local coordinates PQ. So why is it quantizing? Why does it ordinarily quantize R2? Because we know this is a one loop integral. So oh, so, only the integral, quantizing the tangent space of whatever phase space, matters to one loop, and this is why, the phase space, the effective phase space is R2. But, due to the Hamiltonian being negative, so by Hamiltonian, I just mean the mass term here, where the Hamiltonian would sit in the phase space path integral. The integral is defined with Wick rotations, or it has to be defined with Wick rotations to be finite, so that P and Q are pure imaginary. So therefore, the space actually being quantized here is the imaginary slice R2 imaginary of the complexification C2 of R2.
Sorry, I didn't quite understand. So I thought in the previous slide, you posed the problem that how is it that rotating the contour is
Yes.
what you should do,
Yes,
starting from this real contour, right?
yes.
And now
That was not a complete explanation.
Okay.
I didn't, yeah, I have to, there will be many slides on that. It takes some time to explain why.
But now what is it that you explained?
I'm stating the answer from a single brane. And just flashing what you would get from a phase space path integral treatment for these modes.
Basically, you get a harmonic oscillator that is wrong.
Wrong sign mass, yeah.
And then, so can you just then describe that this is what you should do? How is it that you're explaining?
I didn't
It's
explain,
not here. You will.
Okay.
yes.
He's telling us what manipulation works,
Yeah.
and then he will explain why it's there.
To see why this is the correct contour, we need to understand how the quantization of R squared imaginary for a single maximal giant fits into the problem of the quantization of the full phase space, which I call MBPS. In the half
So
BPS
far we've been doing path integrals, compute tracing to the power -θ.
Yes,
I can think of this as a trick for computing the path integral.
yes,
Okay. And at some point, maybe you'll make contact with actually Lorentzian phase space of the Lorentzian problem.
yes. So
Okay.
the phase space that I will use is actually the phase space of this Lorentzian problem, which was studied namely by you and with others, including Davide and Beasley. So it was argued that the phase space of D3 giant gravitons is given by the CP infinity. So with these techniques, you can consider up to 8 BPS sectors. I'll just be more explicit with the half BPS sector, but if you're familiar with this construction, then it's very clear how this will be generalized to the 8th BPS sector. Okay? So they argued that the phase space of D3 giant gravitons is given by CP infinity equipped with a symplectic form, which is in the same cohomology class as this symplectic form, where omega fs is the Fubini study form on CP infinity. So the idea is roughly that the homogeneous coordinates Wn on CP infinity are coefficients parameterizing an arbitrary holomorphic surface viewed as the world volume in one complex variable z. So this is invariant under rescalings of all of the w's, so it's a homogeneous coordinate. The coordinates Wn have R charge equal to the subscript of n, the subscript of W. It was shown that an exact quantization of this phase space at finite n yields the half-BPS Hilbert space and the partition function. And this is generalizable to the 8th BPS sector.
Sorry, so here there is no, here everything is with positive sign, right? The only issue comes when you kind of factor out the infinity part, pull out the any infinity part, right? And then expand, then you start getting big signs.
So this they use an exact quantization method. So it was not a path integral quantization. It was algebraic.
Okay.
Counting sections of holomorphic sections of line bundles and quantizing
I'm
it.
saying there was no -1 to the sorry,
No.
there was no minus sign to be
No,
explained here, right?
no. So the exact quantization gives you just the Gates theory answer on the nose.
So now you have to figure out the analog of pulling out this Z infinity piece and then.
Yeah.
What does that mean for the quantization formula?
Right, yeah. So the phase space path integral will naturally will turn out to give essentially the kind of expansion you want with minus signs.
What is N here in this quantization? Because the answer depends on capital N.
Oh, capital N is the unit, so this coefficient of
Okay.
this some unit normalized symplectic form, which is canonical on CP infinity. So there's a factor of N sitting out. You can alternatively view the system as a charged particle on the CP infinity with N units of flux across any of the CP1s inside CP infinity. So there are different versions of the problem that we can state. So we're interested in the path integral formulation of the statement, and the Euclidean phase space path integral quantizing CP infinity is this. So we have fermions because we're lifting the symplectic form as part of the action. So in local coordinates on the K patch, so there are infinitely many patches. So for CPN, you would have K going from 1 to N, but then here we have CP infinity. So these are the local coordinates that we're using to express this quantity explicitly. And this is the symplectic form, which you can see is lifted into the action.
What is psi?
Psi is some auxiliary fermion that, it's just this fermion term comes about because you've lifted the square root of determinant at every time to the action.
So you're manufacturing forms by quantizing fermions, is that?
Space measure.
Yeah, this is just the measure of the integral.
Oh.
Yeah, this is Pfaffian of Pfaffian omega in the phase space path integral.
All right, thank you. Thank you.
The Euclidean version.
So the size never have a dot.
Yes. I mean, you can do because this integral happens to have some nice properties. You can introduce dots by introducing Kierkegaard terms, but just on its own it doesn't have any dots. So this has some nice properties. There's a hidden supersymmetry relating the z's and the psi's. Once we introduce a chemical potential, the supercharge action turns into the equivariant differential, where the vector field V generates a symplectic morphism, preserving the symplectic ones. So this is a condition for the Dussermatt-Heckman localization to hold. So the path integral may be evaluated exactly as a sum over fixed points and saddles, fixed points or saddles. Oftentimes they happen to coincide. And they're one-loop determinants. So the second property is that the saddles of this path integral that respect periodicity and Euclidean time are after you introduce mu. Here we haven't introduced mu yet. Constant maps to the origin of each patch, UK. So these points are also the U1 isometry fixed points on CP infinity. There's an infinite, semi-infinite line of these fixed points. And the path integral can be expressed exactly as a sum over these contributions from the patches. So when we twist the periodicities by the chemical potential mu, then there are, if you work out the charges, which are induced from the charges of Wn, the homogeneous coordinates, there are a finite number of modes with negative R charges, which gives you a negative Hamiltonian, and an infinite number of constant modes with positive arbitrary, which gives you a positive Hamiltonian. So on the K patch, there are 2K negative constant modes and an infinite number of positive constant modes near the origin of each UK.
You just so that you know, there's no time limit. So
Okay.
please take your time.
Okay. So to understand the contours explicitly, let's restrict attention to CP1 inside CP infinity so that we can actually visualize the problem whose north pole coincides with the origin of the 0th patch and the south pole coincides with the origin of the first patch. So the north pole action in local coordinates has 2 stable directions, and the south pole action locally has 2 unstable directions. This coincides with the BPS space action. So the south pole action is, what I flashed as the BPS space action for a single maximal giant. So if we include the higher terms in the sigma model, forgetting the fact that this problem is one loop exact, the Lefschetz thimble that you can work out associated to the north and south poles would look like this. So the path integral, if you computed the path integral in the patch around the north pole, that would quantize this thimble, this blue thimble, which covers the CP1, and then nearby the south thimble, so nearby the southern saddle, goes off to infinity in the imaginary direction. So this is the that's the thimble, or the steepest descent contour. More precisely, the steepest descent contour is the space of loops in this the blue circle.
Right, you're going too fast for me, sorry. When you talk about a steepest descent contour, you're talking about it for full path integral.
That's right, yes.
Isn't that a very complicated problem?
That's right. So, that's right. So, but we want to, so, our saddle points were at, were constant maps
Okay,
to the north and south poles.
yes,
Right. So in that case, the problem of, the Lefschetz symbol, become simpler.
because it becomes mode by mode. No, it's not, these are.
Um,
Yeah, still it's a very complicated nonlinear theory.
That's right. Yeah, but if you work out okay, so this is the constant mode symbol.
Yeah, that's an integral, so it's clear.
Yes, but the non-constant modes are like a periodic. So the non-constant modes give you time-dependent trajectories on the surface. So the phase space.
It's only the integral over the constant mode that needs to be looked at carefully.
Yes.
Rest is simple.
Yes, or there.
This is just, we are doing quantum mechanics on.
Yes,
this,
so the-
right?
Yeah, so the constant modes are the constant maps of S1.
As a function of time.
Yes.
Okay.
So
But just, I mean, when I look at the steepest descent contour.
yes,
Or the supersymmetric quantum mechanical problem.
yes,
There is some, this can be phrased in terms of Witten's Morse function and that kind of thing.
yes,
So you're just looking at just function, right? It's a function defined on CP infinity.
Yeah.
And you want to now look at its steepest descent. Yes?
that's right. But there's also time, there's also, there are also higher modes, higher Fourier modes in time. So in general, if we don't localize to, so here we sort of forgot about the fact that this problem is one loop exact. So in general, you'll have the higher temporal modes playing.
I thought, the lines that would go from one saddle point to another saddle point would be thought of as instantons, classical instantons.
Yeah. Mhm.
So that's the time, but that's the time parameterizing this path. So I don't why able to understand what this constant. Usually we talk about those modes in space, right? But this is the full space.
So yeah, so you're talking about the Hamiltonian problem of so for the nonlinear sigma model on some compact target space.
So I can just think of some manifold, okay, it's three-dimensional, but I can focus on this, as you said, CP2 part. And then
CP1.
start looking at a CP1 part, and then start looking at sequence and contours from that, right?
Yeah, so here I've just illustrated the contours for the constant modes.
Yeah, this constant mode is what I want to understand. Why are we saying constant or not? It's just quantum mechanics on this.
I mean, typically the thimble will be infinite dimensional, right? So in order to be able to visualize, I'm just illustrating the constant modes.
Infinite dimensional because the phase space is infinite dimensional.
No, because there, you have to integrate over every Fourier mode.
He's the path integral is doing the Z of P.
Yeah.
At the moment, he's just showing us what happens for Z.
But usually you take that as a parameter of path, right?
Yeah, but you could imagine taking Z of T and Fourier transforming and think of it as a product of the integrals. One for each Fourier mode.
Okay.
And he's telling us what's happening for the zero.
But the way at least Witten does it in this mode theory paper, you just consider these paths parameterized.
Right.
I mean, that parameter would be like a map to T.
Right. So
And those would be classical instant counts from one saddle to the other saddle.
right. So this is sort of an analog of an instant count. I haven't used the language of fermion number, but there's clearly some connection because you have a set of unstable constant modes here and stable constant modes here. Yeah, there are differences in details.
Exactly this problem, is this exactly the same problem that you would get for quantizing coadjoint orbits for SU2?
Yes, I believe so. That problem is one loop exact as well in path integral formalism.
You can press the bar below. The
Okay.
two bars, just press any of them.
I think I can just write here and if that's visible. So in that problem, so if you're getting if you're computing the SU2 at spin J character, then the contribution from the North Pole will look like this. So spin N, okay, minus the contribution from the South Pole. So each of them are each of these quantities that you would compute at the North and South poles are infinite series. Why is that? Because if you're quantizing some non-compact surface, then you're going to get infinite number of states, right?
Just harmonic oscillator.
That's right. Yeah, just harmonic oscillator. Because in the end you're actually interested in quantizing this compact phase space, you end up getting a Laurent polynomial. So this is the path integral perspective of this problem. That you're canceling out two infinite series computed from North and South poles. Okay, so that's the blue surface is the zero mode thimble around the North Pole, which goes off to infinity in the imaginary direction. So since the surface you're quantizing is non-compact, you're going to get an infinite number of states at the North Pole. But since we're actually quantizing the compact manifold, the southern thimble needs to cancel out this extra imaginary bit from the North Pole. So the correct contour at the South Pole is that which quantizes the imaginary slice of the tangent space at the South Pole, of the complexified tangent space at the South Pole. So this imaginary contour is actually the correct contour if you're quantizing some compact phase space. This appears quite commonly. So even if you're suppose you're doing some saddle point approximation of an integral over some this compact contour from 0 to 1. Then suppose that your action is such that 0 is the dominant answer. There will be some contribution coming from 1, which kind of whose contour goes off in the imaginary direction. So you'll get something like this on the complex plane.
So, sorry, the integral is over one single complex number.
The integral is over. It's a path integral. It is a path integral for quantum mechanics.
But you're only focusing on the 0 mode.
Well, in drawing this symbol, I'm focusing on the 0 mode.
Okay, but suppose I wanted to focus on that 0 mode
Yes.
and draw the thimble. Could you on the complex plane show us what that is?
So okay, so suppose this is the theta. So now let's parameterize things by theta and phi, right? Now we want to integrate from 0 to pi. And well, phi comes along for the ride.
If you don't mind. If you just do your canonical quantization and transfer it to an integral,
Yes.
that would come with some original contour. What is the, please, I'm sorry, you're so stupid, but what was the original variable and what was the contour that you got from taking canonical quantization to a point?
Yes, so the exact contour, so the defining contour of your problem is just the contour from 0 to pi.
0 to pi. And what is the variable?
Theta.
Theta is the angle of, sorry, what?
So theta goes from 0 to
sphere.
pi. Yes.
I see, sorry.
And then this goes from 0 to 2 pi.
Okay.
So pi comes along for the ride.
Yeah.
Theta, if
Okay, so now
suppose
the
you're-
single real number. Great. Yeah, okay.
Okay, yeah, so in order to do some saddle point approximation, you actually have to wiggle the problem a little bit. So you can deform it, you deform the contours that way or this way, but only when you wiggle can you find some nicely behaved, non-degenerate steepest descent contours for this problem. So here I'm just talking about a simple integral, not a path integral over the sphere. And the contour attached to the North Pole is non-compact and goes off in the imaginary direction. The contour attached to the South Pole is also non-compact, but the correct contour of integration is in the imaginary axis because it has to cancel out this bit.
Yeah.
So if the problem is one loop exact, which happens in special settings where you have this electric form and so on, you would just integrate the fluctuations of theta from 0 to infinity around the North Pole, and around the South Pole you'll have to around the South Pole you'll have to integrate the fluctuations of theta from minus I infinity to plus pi to pi.
Great. So now I understand how you associate a Hilbert space with a negative sign to this second term,
Yes.
because it's purely imaginary. Now, is there when it's one loop, exactly, of course, what's happening is clear. But for the first symbol, would you be able to, it's less clear to me that you should be able to associate a Hilbert space with that, because it's going part real, part imaginary. Of course, when it's localizing near the origin, that's no problem, because it goes in the real direction. But in principle, suppose you were not dealing with localization problem, would you be, is there a sense in which you could associate with this funny contour a Hilbert space?
I wouldn't know how to associate a Hilbert space, but one would certainly be able to compute the partition function.
Sure. But I thought hope was to take your calculation of one Hilbert space
Yes.
and decompose it into sums and differences of simpler Hilbert space. One
Yes.
associated with each color.
Right, right.
So it's clear what this other Hilbert space is, I think, because it's purely imaginary,
Yeah.
so it's likely purely real better than
Yes.
but it's something that goes in complex direction, neither pure real nor pure imaginary. It's less clear to me how.
Yeah, the step to, the step further, beyond the partition function to the Hilbert space, I think, I don't understand how that works.
Okay.
But, yeah, we can,
Then close the theta equals 0, it just looks like.
It's tangent space is right. So that's no problem. And since it localizes, in this particular problem, there's no problem. But I was thinking of the abstraction from general lessons
yeah,
to more complicated situations. I won't.
right. So, yeah, so, you can decompose any contour into some Lefschetz simple decomposition with, e to the minus s. If you have this factor in the action, s sufficiently well behaved, you can decompose the problem, the defining contour into sum over Lefschetz symbols. And this should in principle be an exact decomposition.
Fantastic.
Yeah,
And it's
so
chosen such that the imaginary part of the action is constant or not.
Well, yes, that would be the steepest descent condition.
That is
Yeah.
the way it's stored, right?
Yes.
What is the action in one?
Yeah, I do have
Variable.
an example. So the action would, so there's an action for the localizing example, which is particularly nice.
Maybe choose a coordinate.
Yeah, yeah.
Maybe.
The action is there. Okay.
Yeah. Maybe.
Like, something like that. Does this work? Yeah, anyways, yeah, so I might be off by signs or,
But where is this, sorry, how do you get this action?
I didn't derive it. I mean, this is kind of a, this is a model integral that is commonly given in discussions of the applications of Dusser-Mann-Heckman localization.
Okay, no, but in this case, in the case at hand, what sort of steepest descent are we talking about? Meaning, what is the function that is,
The function should be the action.
no, but what is that the action for this? For this problem? Where is that coming from?
For this problem,
Hmm,
it's coming from
one that you had before.
from our problem, like, which was
Can
the
you
phase
flash
space
that?
method. Yes. So this is our action.
So I can just set dots to 0 and just think of this matrix as a single integral.
Yeah, so I mean, if you want to just see what happens to the zero modes, then so this is before you introduce a chemical potential, and then after you introduce some chemical potentials, you'll get these mass or Hamiltonian terms.
And that should be roughly like that.
So this with the higher order correction, so this is just a quadratic action, right? But there's a whole expansion coming from this denominator. So if you include that, then the zero mode thimble would be this. The zero mode thimble would restricted to CP1 would be given by these blue and red curves.
And this K that you had for the various saddle points,
Yes,
the label, that is to be the same as the K label in the sum.
yes, yeah. So our interpretation of the contribution of a single maximal giant is then the following. So ADS5 times S5 with a single maximal giant is a subleading saddle relative to empty ADS5 from S5. The giant has an imaginary thimble that fixes the overcounting by the large enclosed applied spectrum of ADS5 times S5 of the true number of states that exist at finite end. I think this example is a good one. How you get the SU2 characters in the path integral perspective. Should get a finite number of states for any finite n. And since a single giant is itself sitting in ADS5 times 5 with its own KK spectrum, for this ADS5 times 5, the contribution from two coincident maximal giants with 4 unstable modes, unstable constant modes, cancel this redundancy. So it adds back states, right? Because we've over subtracted, have to add back states, and then so on. So returning, if we just return to the computation, the stable directions at the K patch contribute this factor, which is the half-BPS closed inclined spectrum, while the unstable directions with the rotated steepest descent contours contribute in this manner with minus signs, which is the spectrum of open strings on K coincident giants.
And if I think of a sort of rough diagram with the various saddle points and some sort of contour,
Yeah.
You have always been mentioning the contours meeting at infinity.
Yes. Yeah.
So infinity back.
Yes.
Yeah.
Right.
Okay.
So there is a line of critical points. K going equals to 0. So no D-brane, 1 D-brane, 2 D-brane, and so on. So these are fixed points of this n-BPS, which you considered. There are infinitely many stable directions around each of these fixed points at finite K. That gives a KK spectrum. But so the dotted lines, which are schematically these this picture generalized to higher K. The dotted lines are thimbles with that has an overall minus sign, so where 2K is a multiple of 2, is a multiple of 2, but not 4. So the even K's give you positive contributions. The odd K's give you negative contributions. It's this inclusion exclusion phenomenon that the giant graviton expansions seem to be describing.
I didn't quite understand this inclusion exclusion, and I just understand the positive sign because there are 2 minus signs. Right?
Yes.
But in what sense is it inclusion exclusion?
So the first approximation, the first approximation to the finite n answer is the infinite n answer. The second approximation is one in which cancels out the contribution from. I would like to use the word trace relations, but we'll get there. But okay, I'll use the intuition from trace relations. So the K equals to 1 contribution is subtracting out one copy of a trace relation. So the spectrum of one single trace relations dressed by the large n traces, right?
Yeah, from that point of view, it's clear. But
And then
here is path integral. Is there some contour that is being cancelled and re-added or something like that?
that's right, exactly. So
can you draw some picture that makes that clear, perhaps?
So
I mean,
this was meant to make that clear, but it is a direct generalization of this picture. Okay, so the North Pole at K equals to 1 hugs so it only has stable directions. It hugs CP infinity, and when this surface reaches the south pole, so the thimble for the constant mode reaches the south pole. There's one, or there are two imaginary directions, two real imaginary directions, that are being kind of, that are emanating out away from the south pole. But then all the other, the constant, the infinite number of these infinite dimensional constant surfaces are continuing on to this k equals to 2. When it reaches k equals to 2, they're kind of there are 4 constant mode directions that are going off the imaginary axis, and so and these higher k's are canceling out that infinite imaginary bit from that you would get from just considering the k equals to 0 side.
I mean, what I'm, I guess, asking is that if I look at this picture, then it looks like these, the solid guy will cancel the dotted guy for 0 and 1, giving you the contribution, which is an interval from 0 to 1. Right?
This one,
Yeah.
yes,
And then the next guy would be like interval from 2 to 3.
yes.
No, that has been already cancelled. Maybe this picture is not.
Yeah, unfortunately, I can't draw
Okay, it's fine.
higher dimensions. So there's one constant mode direction becoming imaginary, and this the k equals to 2 is what's canceling out that imaginary piece of the thimble. And then, you know, there are 2 complex dimensional imaginary constant mode thimbles near k equals to 3 and so on. Yeah,
That's fine.
I think it's hard to, I'm sorry that I couldn't
No,
have a better illustration, but I think it's just the generalization of what goes on here.
Yeah.
So if you sum over k, this problem was one exact around each of the fixed points, which lie at the origins of the patches UK. So summing over k, we retrieve the half-BPS formula via the phase space path integral quantization of the BPS phase space that was proposed. CP infinity with symplectic form n times the canonical symplectic form. So, although the BPS phase space had many simplifying properties that we discussed, like this hidden SUSY and one loop exactness, it seems reasonable that some lessons from this example will hold beyond these settings where there exists no method of exact quantization. So, and the path integral perspective is seems like a very useful perspective in considering generalizations beyond scenarios where you can use you can quantize exactly some phase space. So the phase space path integrals on compact phase spaces M, whose contour is the space of loops, and M may be decomposed exactly into sum over saddles and their Lefschetz symbols, even in situations where the system is not one loop exact. So being even dimensional, the one loop contributions around the subleading saddles may have relative signs, depending on the number of modes that have to be Wick rotated away from the defining contour. Okay, so so far we've seen that the BPS partition function of giant gravitons possess overall sign, which resulted from the fact that there were an even number of unstable bosonic scalar modes on the world volume. Now, suppose we wish to associate a state counting interpretation for this sum. So then -1 to the k would need to come from a grading in the associated Hilbert space H sub n. But we know that the half-BPS Hilbert space in n equals to 4 super Mills is purely bosonic, and it's graded only with respect to the energy and the R charge. In other words, there seems to be no extra grading that you need, that is suggested by the giant graviton expansion, required to provide the -1 decay. So the obvious question is, how is the BPS spectrum ZK of D3 giants in ADS 5x5 encoded in the boundary? So to answer this question, let's try to identify the states, in quotes, in the boundary gates theory that possess an extra grading and also reproduce this spectrum. They cannot belong in the physical half-BPS Hilbert space. These, whatever, if there is a state counting interpretation, well, the purpose is to cancel out the redundant counting of states at large n. So we can obtain clues regarding these states by examining the mode expansion in Z of the determinant operator in UN n equals to 4 super mills, which is dual to a family of D3 giant graviton solutions. This auxiliary parameter Z, which is different from the other Z's, has an interpretation as the bulk insertion point of the brane on the plane transverse to S3 and S5. So the fluctuation modes in Z of the determinant operator can be written in this manner, but well, for finite n, determinant of Z minus X, where X is the matrix, it's going to be a polynomial in Z. So the negative powers that you get, this negative, the negative powers that you get here, that tail should be equal to 0. So those are the null states. So these are the first few coefficients.
To explain why you introduce determinant at Z minus X.
This parameter, this is classically dual to brane solutions. And Z parameter is the size of brane solution. So for large Z, you have a small brane. For that's the classical. That's the interpretation in terms of the classical brane solution.
Pn is determinant X. No, I mean larger, P larger. So what is P larger?
So these are coefficients in this large Z expansion. But then we know that the P's which appear with negative powers of Z need to be set to 0. So they actually happen to, so this is a generating function for trace relations. Right, so yeah, so this is a trace relation at n equals to 1. This power is a trace relation at n equals to 2. This power is a trace relation at n equals to 3, and so on. So right. So the negative powers of these must be multiplied by coefficients which are trace relations. So the states constructed by acting with these piece of n 1 and greater on the vacuum are the finite n null states. Right. These are null states that need to be separately accounted for only if we decide to work with the gauge invariant variables rather than with matrix components in which the trace relations are automatically accounted for. So let's account for the null state constraints cohomologically. To impose, so all I'm going to describe here is just a way to change variables at the level of the state space in n equals to 4 superangles such that the quantities that you see in the partition function are reflect what we can compute in the bulk, okay, which are the giant graviton contributions. In the bulk, we don't know how to see a strict cutoff at the finite value of the spectrum.
So are you going to now change path integrals to traces?
So I'm not discussing the path integral interpretation of this.
Okay.
That was earlier, but I'm just gonna discuss the state space interpretation.
But we could have tried to move to a path integral in terms of an infinite number of traces.
Sure. Yes.
And then impose constraints on that path integral
Yes. Yes.
along these lines.
Yes. Yes. But yeah, in that case, you would have to work with variables which are themselves. You have to work with fields which are themselves the traces of x's.
Yeah.
You have to work
Yes.
manifestly in the gauge invariant variables.
Yes. So I was thinking if the right path integral is in terms of the matrix variables,
Yes.
then if you did a change of variables to traces,
Yes.
then you could change variables to an infinite number of traces.
Yes.
And then impose trace relations.
Yes. Exactly. Mhm.
And then you would have these sort of Lagrange multiplier fields imposing these trace relations.
Exactly. Yes.
So you get a new path integral with many more fields.
Yeah.
Okay, you're doing a canonical version of that.
I'm doing a canonical version of the procedure. I don't know how to consistently do this, the path integral procedure.
Yeah.
Do you?
I don't know.
Okay.
It sounds a little, yeah. It sounds a little bit like a toy model derivation of ADS here. Going from field matrix value variables to traces is what ADS-CFT does.
Yes. Yes. Yeah. Yeah. Right. So, so here I'm answering from a canonical perspective. What we need to do at finite n. So on top of working with the invariants, what do we need to impose?
Yeah.
The cohomology of Q hat, which has nothing to do with supersymmetry, it's just some differential, is the half-BPS state space of UN n equals to 4 super unknowns, which is third.
The Woods guy, minus m minus alpha.
Oh, sorry, I didn't explain the details of this.
Something.
This is these are some indices associated with auxiliary ghosts, I, which map to the trace relation. So this is just I'm just stating some cohomological way to implement these relations. Of course, you could have taken them account just by working with matrix components. Then I mean that's the easier way to study the system, obviously, at the low values of n. But I want to make the gauge theory look kind of like what you see in matrix invariance plus constraints, further constraints and so on.
You want to make it look like the bulk.
Yeah, I want to make. I want to. So I'm describing some manipulations that one can do at the state space level of the gauge theory that makes it look like the bulk. So in doing so, you can identify what exactly is the thing in the gauge theory, the state in the gauge theory corresponding to these giant graviton, the states that you got from quantizing the giant graviton.
Yeah.
So that's the goal here. So the UN state space is the quotient of the half-BPS space of states at infinite n by the trace relations. And these are just auxiliary variables, which are anti-commuting, but have the same quantum numbers as what is the trace relation that it's mapping to. And the differential Q hat is just to supplement the infinite n theory for with directions for systematically removing all but the states that remain at finite n. So the states with ghost number k are multi-ghost states, so kind of k chi's and which have the spectrum. So, so the signs must be included because the ghosts chi are implementing null relations. So here we're computing the index with respect to these ghosts, but these ghosts have different quantum numbers from these ghosts have the same quantum numbers as the bosonic trace relation that's mapping to. It doesn't have half integer r or the j's.
So for each of these trace relations, you have these ghosts, right?
Yes.
For each one of them.
For each one of them.
And
also, since there are infinite number of solutions for any finite term.
Right.
Why the reduction in the number of states finite?
The reduction in number of states is not finite, it's infinite. So if you look
At
at
a
the,
certain energy level, the
Yes.
reduction in these number of states is finite, right?
yeah, that's right, yeah.
At a certain energy level, the number of trace relations.
Yeah, both higher boosts contribute at higher level. You can see that from the weight there. So how do I see this weight? Q
Which weight?
to the power kn times q to the power k.
That's just obtained by just computing the charges of these and summing over. So fix a particular number of ghosts, and you sum over a's, which don't overlap.
Which don't overlap. What does
So
that mean?
A1 going from 1 to infinity,
Oh, I see.
A2 going from greater than A1 to infinity,
Okay,
A3 going greater than A2 to infinity, so on.
I see.
So these are null states, or these are null states?
Yeah, these are null states implemented in some particular fashion.
And the fact that product of two chi's contributes positively, the saying that if you remove one trace relation and you've removed the other.
Yeah.
Then you've done overcounted, let's say you want to add them back.
Right, so,
The product of them you remove twice, so.
Yeah.
You want to put that back.
yeah.
Okay.
Because these are multiplied by the infinite n traces, which are themselves subject to the trace relation, so you have to remove the contribution from having two ghosts and so on. Okay, so I'm just describing some,
And this
I'm
n
doing something very simple, like very trivial.
This n is implemented by just saying that you consider ghosts above certain n, right?
Yes,
Because n is like a baseline.
right, and it's the
Only above n.
the baseline. Yeah. So
So let's see, so now. Is there some more direct way to see this map between these ghosts and these symbols, these saddles?
I'm not sure. I would really like to understand it, like especially from the point of view that Shiraz mentioned, which is, working. It was. I think it's kind of a dream to be able to, in holography for a long time, to be able to rewrite the Gates theory in terms of invariance and impose relations on them, etc.
This seems like an ideal place to do that, right? It's very simple, single variable.
So I want to comment on what the identification between the half-BPS states of bulk giant gravitons and those for trace relations in the boundary gauge theory suggests about what a useful way to describe the bulk half-BPS space of states might be. We can organize the space of multi-ghost states with coefficients in this ring of polynomials of traces. So it just means that these chi's have coefficients in the invariant variables into a complex where Vk is the space of multi-ghost states of ghost number k with coefficients in this R.
Sorry, every chi is associated with a particular trace relation, which is a polynomial in X. That's what this.
Yes.
Okay, and what are all these arrows?
So these arrows, so the stuff living in D1, okay, are the single ghost states. Single ghosts tacked on with infinite n traces. Stuff living in V2 are two ghost states tacked on with
So two trace relations
tacked on with all of these.
and anything else.
Yes.
Okay.
Yep.
Fine.
So this R that you call here, that is this CP infinity coefficient of that. Coefficient space there. Is that how you should think of this?
So
The original CP infinity that you're talking about is just that, right?
no, it's not that. So this CP infinity, so n is not the power of CP, right? The CP infinity is equipped with n units of this, of the canonical, symplectic form on ZP infinity. So, if you take the trace over this space R over this space R of Q, that notation. So let's denote this by the R charges by R1. Then, so if you compute this quantity, then you're going to end up with the KK spectrum in the half-BPS sector, which is the contribution of from the North Pole. So this R is a space of states, the perturbative space of states that you can build around the North Pole of this ZP infinity. But then, so the V1 is the perturbative space of states that you can build around k equals to 1.
Yeah.
And so on.
So, how can I understand this picture in terms of relations and relations of relations and so on?
So this is exactly describing, this is an algebraic tool, which exactly is capturing that, what you mentioned, relations between relations. This is a, it's called a free resolution. I'll mention it, but it's a tool which lets you assign a good notion of a dimension to a highly constrained quotient space.
So V1 corresponds to like one relation and like V2 corresponds to relations of relations?
Yes, yes. But the relations between relations are very simple here, right? They're just
So V1 corresponds to one thing that is zero by trace relation and multiplied by anything else, right?
that's right.
And V2 corresponds to two things that are zero by trace relation multiplied by anything else. V3, three things.
Yeah.
So there is this free resolution, as you mentioned, but there is also another resolution where you just work with the generators up to trace x to the n, right? And those don't have any relations. I mean, not matrix elements, but just those. And that is also enough to construct all the states, right?
So the trace is up to power n?
Yeah.
Yeah. Then you have no relation.
So that's also yet another different type of resolution, which is kind of a simpler resolution.
Right. So there is no resolution in that context because there are no relations in that context.
Yeah, so it's just free ring, just a free ring.
Yes.
Already resolved, yeah.
Yes, yeah. But this is kind of special to the half-BPS sector.
Yeah.
Right.
Right,
Yeah.
single matrix.
That's sort of like doing the exact quantization.
Yeah. So a ring admits multiple resolutions in this sense, I guess, right?
So the quotient of the ring by relations admit multiple resolutions. That is in general non-unique.
Yeah.
But it gives you a lower bound on the dimensions of V1, V2, V3 at some value of the charges. So there's a notion of uniqueness to resolutions, and it gives you a lower bound on the dimensions per charge. Okay. So as I think it's evident, I hope, so VK should be identified with the perturbative space of states built on ABS5 times S5 in the presence of K coincident half-BPS giants. So this complex has non-vanishing homology. I call it homology because it decreases the Gauss number, only at 0 Gauss number. Since the image is the space of trace relations with coefficients in R, so H sub infinity is R. The homology at Gauss number 0 is the Hilbert space in the half-BPS sector of UN n equals to 4 supraangles at finite n. I hope it's clear that this is not special to the half-BPS sector.
Sorry, I didn't understand those words, but are you saying that if you do the sums, all you're left with are things without trace relation.
If you take the homology, then
Homology means what you do.
yeah, it's the common use of the word homology.
I just happened not to know it. You could
Okay.
say,
Yeah, so it's so here, I'm claiming that there's only homology, you can think about it as homology equivalently. There's only non-trivial homology at this step, okay? So
homology, which it means something that can be written there, but not as Q1 of something.
yes, so
Yeah.
the kernel is all of H sub infinity, right? But then there's also this image coming from V1.
Thing that does not have a trace relation,
Yes,
a factor of a trace relation, right?
But V1 itself will have similar quotient. I
V1,
mean, it's a complicated thing, right? So you're writing Hn is equal to H infinity divided by Q hat on V1, but V1 itself will be something like some quotient, right? I mean, you have to somehow capture this full chain.
But I thought with plus minuses,
Yeah.
that the things minus those which are one trace relation, plus those which are two, minus those which are three, plus those.
But this equation here just picks up U1, right? V1. So I was wondering how to,
yes,
V2
yes.
and all these other things.
I agree
So
with you.
there you would have, so what sort of thing would you write down for the V1?
Each end only captures a single relation, not like.
No,
of relation.
no, but that V1 already has all that, I think. That's what I was thinking.
Okay.
That's why the final expression becomes so simple.
Yeah.
The V1 itself is kind of, you have to resolve it that way.
Right,
But
yeah.
I was wondering how to write the equation for that, like.
Yeah, it must be a quotient. So in the same way,
Something divided by Q of V2 and V2, right?
yes, yes, yes.
I don't know what divided by.
Yeah, maybe I won't answer that.
Yeah.
Okay, but this is just very similar to what happens with in 2D CFTs on 2D minimal models CFTs on tori. In that case, you have Virasoro descendants of singular vectors, which so those singular vectors generate a submodule inside the space that you get by acting with all the Virasoro generators, and there's some iterative submodule structure.
Yeah. So the character formula has the same plus minus.
Exactly. Yeah. So it's exactly the same idea, but just applied to trace relations. Okay. So namely, these V's are free R modules. That's if you care about if you know what that means. So this means that if we augment the complex with H sub n at the final step, the resulting exact sequence is, so this is, first of all, this is an exact sequence. And it's called a free resolution. It's called a free resolution because all these spaces on the left, except for H sub n, is they're Fock spaces. So it's the free resolution is a procedure of replacing a highly constrained quotient space with a sequence of unconstrained Fock spaces whose generators represent the constraints on H sub n. So why am I mentioning this? So the resolution seems to give a precise relationship between the half-BPS space of states of UN n equals to 4 superangles at finite end, and this complex built out of the perturbative states, whose interpretation is the perturbative states built around ADS cyclone defined with k numbers of giants. Yeah, so this complex is identified with the bulk half-BPS space of states, perturbative space of states in ABS 5 this is more like a large Hilbert space whose homology yields the physical Hilbert space. In the end, you have a reduction to the true space of states, which we know is H sub n, but this is I think this is a useful way to, possibly useful way to think about the bulk space of states at finite value of n. And the resolution, this says that the states of certain bulk D-branes are encoded in the relations between the single trace generators in the boundary gauge theory at finite n. So it's a property of exact sequences that the alternating sum of dimensions of spaces in the complex vanishes. So you can express the charge spectrum of H sub n in terms of an alternating sum of the charge spectra of Vk over different values of k, which is, this is the content of the giant graviton extension. And as I mentioned earlier, this shares its origin with the kind of complex type of submodules that you have in the RST approach to minimal models on the torus, where you also have some alternating sign formula with an overall coefficient, the character of the space that you get by acting with all Virasoro generators. Maybe I can speculate a little bit. What's the bulk interpretation of this differential, which we don't know?
Sorry, what's the analogy of this A brane in the case of Virasoro, the case of 2D CFT that we're talking about?
Yeah, so that's like the kth submodule inside. So you have a structure of nested submodules in these minimal model CFTs.
So you have this null vector, let's say,
Yes.
in this Virasoro module.
Yes.
Now you are saying that Q acting on that singular vector will give you, let's say, second module. Is that right?
The null vector is itself a short representation. It has its own null vector,
Yeah.
which is itself a short representation, has its own null vector. So you go K times that.
So that's like A graviton. Is that right?
Yeah, but
Yes, right. Okay.
so the kth null vector of null vector.
Does everything admit a free resolution?
Sorry.
Does everything admit a free resolution?
Yes. Proceeding up to some charge cutoff.
Proceeding?
If you impose some charge cutoff, you can always find a free resolution if you're considering a setup of this type where you have polynomial ring quotiented by relations,
Yeah.
you can always find a free resolution. But actually computing them, you have to impose some cutoff on the charges. Because there are infinite number of states. So, anyway, so what would be the bulk interpretation of the differential Q hat if we took this seriously? It maps the half-BPS state of K coincident D3 giants to linear combinations of K-1 coincident D3 giants with coefficients in these traces, which don't vanish because which are trace relations. So since we're working with the infinite n variables, these are not vanishing. These are trace relations of charge n plus a. And so a natural interpretation for Q hat is that it's an instanton, similar to the kind of idea you, Abhijit, mentioned, that interpolates between a pair of vacua labeled by K and K-1 wrapped D-branes in ABS 5 times this type. So, but it needs to consider charges. So it would map to the vacuum labeled by K would map to the vacuum labeled by K-1 dressed by a set of gravitons which fulfill such that you preserve charges. Okay, so the lessons from the half-BPS sector are the following. We can identify the bulk space of states with complex of auxiliary ghosts that implement the finite end trace relations via cohomology, and where the physical Hilbert space is given by the homology. This complex furnishes a BRST resolution or free resolution of the finite end space of states of the boundary gauge state. And I think although the bulk computations in the half-BPS sector relied crucially on supersymmetry and the presence of a weakly curved gravity limit, let me argue that the lessons above do not rely crucially on those properties. We know that trace relations between gauge invariant operators are present in any finite end gauge theory with adjoint fields. So at least in the free theory, it's always possible to write the space of states of this theory as that of a U infinity gauge theory, which is supplemented with these auxiliary ghosts for trace relations that would have been present at a value of n. So in general situations, you would have a ring like this, okay, acting on the vacuum, and the trace relations may satisfy non-trivial relations among themselves, which is expressed. So this is what I mean by a non-trivial relation between trace relations. Yeah, so in general, it's difficult to compute this resolution. But assuming that one has computed this resolution up to, which is called a Kozel-Tate resolution, up to an energy cutoff, the Lefschetz trace formula relates the trace taken over H sub n with an alternating sum of the traces taken over V sub k. So for example, the free partition function of UN gauge theory on S1 cross S3, once you've constructed a resolution, is equal to the alternating sum of the free thermal partition function over Vk. And this also gives you a tool to relate the thermal coordinates. This identity, which we found for the case of the giant graviton extension, the superconformal index is a special case of this more general consideration of finding resolution over the large N ring R. So the Lefschetz trace formula appears to provide a gauge string map at lambda equals to 0 at finite n, where the bulk observables are computed by taking the alternating sum of the expectation values in an ensemble of states built on each open string vacuum. So,
Minus R equals to 0.
I
Suppose.
yes.
What are you calling Lefschetz trace formula?
So this expressions of this form are called Lefschetz trace formulas.
And the BK, the special thing about it is that the box space.
Yes. So the point is how
Box space always with infinitely many oscillators.
it always has infinite many oscillators. The KK spectrum, it's stressed by the KK spectrum with additional generators with coefficients in the KK spectrum, like the KK states, right? So yeah, it'd be nice to understand.
So is it that once you first, as we saw earlier, there are multiple free resolutions. For example, in the half-BPS case, there is this resolution, which is infinite spectrum at infinity, plus minus, these are relations, each of them also have this infinite tower and so on.
Mhm.
And then there is this another way of writing, which is just n generators, right? For Fock space, finitely many oscillators.
I would say the latter is not a resolution. The resolution,
Well, it's a clear resolution because it's already resolved, right?
okay,
So
but
it's
what are you
it's a
resolving?
free to begin with, right? It's a free
Okay.
thing to begin with. Meaning there's no, it's a regenerated freely,
Okay,
right?
So-
So in that sense, so is it that once I pick up in some sense the first part? I don't know what I would say, but the first part, that I want to think of this ring as starting with an infinite n ring, infinite n spectrum,
mhm,
and then start adding relations and so on. So
mhm.
once I fix that first part, I guess this the later what I have to do is fixed.
It's fixed up to trivial ambiguity. Like, I mean, you can always adjoin to a resolution to a complex, so let delta be the differential, which I called Q hat before. So let delta map chi2 to C. Let delta map chi to C. Okay. So let this state have ghost number 2, and this state has ghost number 1. You can always adjoin this this long representation like states to a complex and not change its cohomology. So there are ambiguities, but there is a lower bound for regarding the number of states in the VK for a given choice of for a specified value of the charge. The half-BPS sector happens to saturate this now. Okay, so yeah, so some remarks for the future. It'd be nice to compare the gauge and string theory results directly at lambda equals to 0, possibly by understanding control boundary conditions of tensionless strings and ADS5 and this5, although there much work needs to be done in that direction. Thank you.
Sorry, one question. So does this also explain in this Imamura and the formula that you guys have that the denominator is the same for all these plus minus terms? It's exactly the same, not just that it's an infinite product. So why is it
Denominator, I don't understand what denominator.
is Z infinity that
Yes,
you have to put out
yes,
and then
yeah.
So that's the Fock space, right?
Yes,
That is
yes.
happening at every level,
Right.
right?
Yeah.
So why is it that the oscillators have the same charge for each of these decays?
We're working over with coefficients in some ring, and the character over, the trace computed over that infinite n vector space, which is R, is going to all be the same. And since V's are free spaces, so they're Fock spaces, the character of R, so the trace of R is going to factor out simply because the V's are free, so-called free R modules.
No, but the free R model would have also allowed you possibility to have those generators different charge, right? Different charge. Isn't it possible? I mean, not necessarily just in the BPS, half-BPS case, but you have this more general formula, right, which is applicable for higher, less BPS states. So there also, this Fock space is made out of somehow generators of the same charge, which you pull out as Z infinity.
So the generators of those modules do not belong to R, they have coefficients in R. So the generators are these ghosts.
Yes.
Which have different charges from the, one VK to another VK prime.
Different charges.
Different charges, yeah.
But the denominator structure is the same, right? N equal to 1 to infinity, 1 minus q to the n inverse.
This is just the character for the coefficients of those generators, which factor out because there are no, because the VKs are free R modules. But the generators of VK as modules, as R modules, have characters which are different from one K to another. Not sure if I'm answering your question.
I mean, I was thinking that the different part is this q to the power k times k plus 1 by 2, right?
Yes. Oh, and there's also a denominator.
The denominator is the same.
No, there's also a denominator.
Like the sum of each trace relation. Is it even that you can have one trace relation or two trace relations, but there are many different relations.
Oh, I see. So the denominator is also there. Okay, sorry, I missed that. Okay. Okay.
Yeah, so I mean, there are going to be infinitely many generators because there are infinitely many trace relations.
Yeah. Right. Okay.
Okay. Yeah, thanks. Are there any other questions?
Maybe that question.
Okay.
Sorry, just one very general question. You have this basic philosophy that you take this path integral
Yes.
and you break it up into saddle points and then thimbles, and then associate a Hilbert space with each
Yeah.
thimble.
Yeah.
Now, I wanted to ask whether it was always that, let's say that the whole thing gives you, real Hilbert space with integer coefficients. Is it clear that each thimble also always gives you
No,
Hilbert space with integer coefficients?
it is not clear. If you don't have a one loop exact integral around the saddle, then you'll have a 1/n expansion.
Yeah.
So I would be able to compute the partition function, but I wouldn't really know how to interpret it from a state counting perspective in general.
But is it not that if you have imaginary contour, then you will pull out an eye and think of it just as a x to minus sign for ordinary quantum mechanics?
But I was wondering, forgetting about the sign, whether it becomes 1.13, the coefficient of integer.
Yeah, so if what I said is true, then no, right? So I didn't quite understand.
But I think he was saying that, you will get a perturbative expansion. And how can a perturbative expansion be consistent with integer coefficient? Right, because you change things a little bit. So, is that right?
That was that was my guess.
Yeah. So then it's nice to distinguish situations where you do get, here you did get Hilbert spaces coming by them.
Yeah.
But of course, it was a very special situation. And those seem like the most interesting cases where it's not just some path integral manipulation, but you can actually associate a Hilbert space to each center.
Yes.
Would be nice to have a criterion for when that was the case.
Naively, one would think that because of the tails of the 1/n expansions,
It's almost never the case.
it's almost never.
So one loop exactness is what you.
I mean, yeah, in all the cases that we know, yes.
Right. Right.
I mean, even the ordinary saddle will not give you integrality, right? In that case, the ordinary expansion, not necessarily about an instant of some other saddle point, but right.
I mean, it would if there were no other saddle. If there's just one thimble, that's the whole thing, and that's it. Yeah, right, because the full answer gives you integers.
Yes.
So this would be building up to an integer. But
Microcanonical.
yeah, the coefficient of e to the power minus beta E1
Yes.
would be an integer in the end.
Yeah.
The question is whether if you have two of them, it also builds up to an integer here and builds up to an integer there. But different one. Totally clear to me that it couldn't happen, but of course it's not like a conspiracy.
It does, yeah.
But I thought you could just think of each individual contour as a proper quantum mechanical system, right? Up to minus signs.
Yes.
So then if you want to compute thermal partition function along each of those contours, then why not? It does seem a bit surprisingly strong. Why wouldn't you get integers?
I mean, I believe you, so, yes, I do think you should get into this.
You should.
Yeah,
For the whole thing,
For
for
the-
thimble,
actually, yeah. Yeah, based on your comment, it would seem that you would get integers for everything. Although. Although I'm not sure how to see